Okay, so let's go through these examples, looking at Lenz's law and figuring out the direction of the induced EMF. The first example is you've got a magnetic field coming out of the screen, out of the paper, that, and you've got a loop of wire that's being pulled out of that magnetic field. So, if you are pulling the coil out of the magnetic field, you are decreasing the flux in the outward direction. And so Lenz's law says that the induced EMF is going to be equal to some negative rate of change of that flux, which means it's going to oppose that decrease. And the way you oppose a decrease is by creating your own magnetic field in the same direction. So if the magnetic field is out of the page and you want to oppose that decrease, you create your own magnetic field out of the page, and that is done by a current that wraps around the loop in this direction by the right-hand rule. So that means that the direction of the current in this loop will be like, I'm having trouble with my pen here, hold on, like this, around that way, okay? That current that goes around will oppose the decrease pointing out of the page. Next example. You've got a magnetic field, a uniform, constant magnetic field pointing into the page, into the screen, and you have got a loop that you're going to shrink in size that exists in that magnetic field. So the magnetic flux is into the paper, into the screen, and shrinking the loop will decrease the flux through that loop. If you're going to decrease the flux through the loop, you want to oppose that decrease by creating your own magnetic field in the same direction into the screen, which means the induced EMF is going to be around this way via the right-hand rule. This is the direction of a current that will create a magnetic field that opposes the decrease in flux. Okay? Example C. A south magnetic pole moving from below up toward the loop. I feel like it might be easier to think about this one if we draw it sideways, or draw it in 3 dimensions. If you've got a magnet with a north pole and a south pole, let's switch to a finer pen here. North, south. Remember that magnetic field lines go from north to south. So at the south end of a magnet, the magnetic field lines are pointing this way. Right? So that means as you move the magnet into the coil, there's going to be an increase of flux in the into the screen direction. If this is my loop and I'm moving the magnet through the loop that way, there's going to be an increase in the flux in the direction pointing into the page. Okay? If this was a north magnetic pole, it would be reversed. So if there's an increase in the flux in the direction into the screen, and we want to oppose that increase, we do that by creating a magnetic field in the opposite direction, so out of the screen. And the current that will create that magnetic field out of the screen is a current that goes around the loop by the right-hand rule in this direction, around the loop this way. So the induced EMF and the current will be around the loop that way, creating a magnetic field out of the screen to oppose the increase in magnetic field into the screen. The next example D. A north magnetic pole moving toward the loop in the plane of the page. So the loop sits in the plane of the page, the magnet sits in the plane of the page, and the north magnetic pole of a magnet is moving towards the loop. Again, if we think about the magnetic field at the north pole of a magnetic dipole, what does that look like? The magnetic field lines go from north to south, but they're three-dimensional, so we have to kind of picture these magnetic field lines going from north to south, but in all directions around this. Oops, sorry, that was the wrong way. Those last two were wrong. From north to south. So in 3 dimensions, if we've got a loop like this, and this is approaching that loop, feels like to me the issue is the net magnetic flux through this loop. The normal vector to this loop is out of the page, right? And the direction of the magnetic field, due to most of these field lines, is going to be this way. And B dot dA is going to be 0. So the flux, as this moves through in the parallel direction, is going to be equal to 0. Is that right? Yes, that's right. I checked the book. I cheated and paused the video and checked the book. So the magnetic field lines in this case are all in the plane of the paper, and the loop is in the plane of the paper. So B dot dA, the dot product between the magnetic field vector and the normal to that loop, is 0 the whole time. So as this magnet goes by, the change in flux will be 0. The flux will be 0 the whole time. If we rotated this loop this way so that it was on edge, there would be a changing magnetic flux because the field lines would go through that loop. But in this direction, the field lines and the loop are always perpendicular to one another. One last situation, which is, imagine a loop that's vertical rotating within a magnetic field that points towards our left. So the magnetic field points this way. You've got a vertical loop that's spinning like this. What does that do to the flux? Well, we just saw that when the plane of the loop and the magnetic field lines are in the same plane, the dot product is 0 and there's no flux. But as this rotates towards the side, from this orientation to this orientation, let me just draw the whole thing again. Okay, so here's our magnetic field, here's our magnetic field, here's our magnetic field. As we rotate from this situation to this situation, the leftward flux through this loop is going to increase. Okay. In order to oppose that increase, the loop is going to generate a magnetic field of its own towards the left. So the induced magnetic field will be, the induced EMF will be in such a way that its magnetic field points towards the right to oppose that magnetic field, that increase in magnetic field towards the left. So that means that initially the direction of the current through the loop will be in this direction. Okay? If it's spinning out of the page towards us, in order to oppose the resulting increase of the flux in this way, it's going to generate a magnetic field that way, and it does that by creating a current around the loop that comes out of the board towards us. As it continues to rotate, the flux will decrease again, and it will oppose that decrease by creating a flux in the opposite direction. So as this makes a full rotation vertically, we might expect something like this. And one half of the turn it opposes the increase, the other half it opposes the decrease, and the EMF induced in that loop will actually be in one direction, then the other direction, then the other direction, then the other direction. This, by the way, or something very much like this, is how we generate alternating current. If you take a coil of wire and you spin it in a magnetic field, you get an EMF that goes first one direction, then the other direction, then the other direction in the wire. So if we connected this wire to a voltmeter, we would see the needle go one way, then the other way, then the other way, then the other way, as that current moved back and forth. Okay, so go through those examples with your right hand waving around in space until you understand them. I'll post a few more conceptual Lenz's law problems to the homework just to practice. And now we want to look at quantitatively how would we actually calculate not just the direction of the EMF in one of these situations, but the amount of EMF, how much voltage is generated by this change in magnetic field.